Hello. In this episode, we are going to solve this separable differential equation, and we are going to see why this is separable with an initial condition. So what you see on the left, this one is called initial condition, and I'll explain that later. That's called initial condition. Okay. So don't worry about initial condition for a moment. Just try to solve this separable differential equation. So remember, separable means I can separate all x. So I should be able to write this as some function of x times dx equal to some function of y dy. So if you think about that, first I can bring, for example, I can bring one of the term on the other side. So let's do that. Okay. So I have y e to the negative x dy equal to negative x dx. So I move x dx on the other side. So the problem here is this e to the negative x on the left. I should not have e to the negative x on the left, right? I should only have a function of y. Again, which side you put x and which side you put y, it does not matter. So here we put x on the right and y on the left. So how I get rid of this e to the negative x? You know, in this case, you can just multiply both sides by e to the x. Because if you do that, e to the x and e to the negative x is e to the 0, which is 1. So e to the x times e to the negative x is e to the 0. I want to remind you, when you multiply, you add the exponent, right? So x plus negative x is 0. And anything to the power 0 is 1, except 0 to the power 0, of course. So if you multiply this out, you get y dy equal to negative x e to the x dx. Now you take the integral of both sides. So the integral on the left is 1 half y squared, and we're only going to add c on the right, and I explained that in our last example. So you don't have to add plus c1 on one side and plus c2 on the other side. You can just add c on one of the side. So I'll just add c on the other side. Now for this one, we're going to do in a separate places. So this you need to use integration by parts. So let's actually do this in separately here. So let's actually do that. So let's do this here. So this will actually a review of integral by parts. So let's see, you can do that. So remember, you write u and then you write dv. So one of the factor is u, one of the factor is dv. So let's say if you want, you can put this negative outside. So this negative, you can put it outside if you want. Let's actually do that. So that will make things easy. So I'm going to put that negative outside. So don't worry about this negative right now. Just concentrate on this much. So here, this factor is u and this factor is dv. So my u is x and my dv is e to the x dx. So for the eu, you take the derivative. So du is 1, derivative of x is 1, but you have to multiply by dx. So 1 times dx. And here you take the integral. So the integral of e to the x is e to the x. Then the formula. So let's first copy this minus sign. And I better put a big parenthesis. So minus has to go everything inside this parenthesis. So it's a better, whenever you have a minus sign, always it's a good idea to put some bracket or parenthesis. Okay. So remember the formula is uv minus integral of v du. So in this case, uv, so u is x, v is e to the x, minus integral of v is e to the x, and du is actually equal to dx. So I get x e to the x minus the integral of e to the x is of course e to the x. And finally, when I distribute the sign, I'm going to write e to the x in the beginning and then minus x e to the x. So that's the integral, and of course plus c. Okay. So let's copy that on the top. So my answer is e to the x minus x e to the x plus c. That goes here. Actually minus, forgot, minus plus c. So make sure I copy it correctly. E to the x minus x e to the x plus c. Excellent. So that is my answer, and that will be, and this will be my implicit solution. Remember, the implicit means the y is not solved in terms of x. So that's an implicit solution. So let me copy that. Let me copy that here. So that is what I have here. Okay, very good. So that's my implicit solution. Very good. Now the question asks you, use this initial condition, and what does this mean? So look at this initial condition. The initial condition says y of 0 is equal to 1. Okay. So think about this for a minute. Remember, c is the arbitrary constant. So your c can be any arbitrary number. So if I replace c by 5, that gives you a solution to the differential equation. If I replace c by -7, that's another solution of this differential equation. So you have infinitely many solutions. For each value of c, you get a solution. So there are lots of solutions. Out of this infinitely many solution, there will be one particular solution that also satisfy this condition, that when x is 0, y is 1. Again, I'll repeat. This one is sometimes called the general solution, one that has the c. So that's the general solution. It's infinitely many solution. So the general solution is always infinitely many solution, because for each value of c, you get a solution. But the one particular value of c will also make this true. So I need to make sure, out of this infinitely many possible solution, which one also satisfy this initial condition. In other words, when x is 0, my y is 1. Another way of looking at it geometrically, this point 0 comma 1, right? My x is 0 and y is 1. The solution has to go through this point 0 comma 1. That's like a geometric way of looking at it. Okay, first let's look at algebraically. Very simple. To find c, you replace x by 0 in this example and y by 1. So here you are going to replace x equal to x by 0 and y by 1. Can we do that? Let's do this. So I'm replacing y by 1 and x by 0. And I'm writing down every single detail so nobody get confused. And then you solve for c. So 0 times anything is 0, so that's 0. E to the 0 is 1. This side is half. So what you have is half equal to 1 plus c, or c equal to negative half. So for that particular c equal to negative half, the solution that we get, so I replace c by negative half here, and that will be a particular solution or a specific solution that also satisfy the initial condition. So you have to So we have to copy everything, and I have to replace c by negative half, and that will be my final answer. So let's do that. So I'm going to copy the entire solution. 1 half y squared equal to e to the x minus x e to the x, and then instead of plus c I have to put minus half because my c is minus half, and that is my final answer, and that will be called the specific solution. So we have general solution. If you don't have the initial condition, then you stop here. Your general solution, that's your final answer. But if you have a initial condition, you use the initial condition to find the value of c, and then you substitute that value of c into the general solution, and that will give you the specific solution. A geometric way of looking at it is, out of all the value of c, which one the graph goes to this point 0 comma 1. So you can use GeoGebra to experiment on that. So I'm going to show you that in the GeoGebra. So let me actually open GeoGebra. Let me 1 second. Open GeoGebra. So this is the GeoGebra. So I'm going to put my function here. So you can just Google GeoGebra, or you can just go to geogebra.org, and it's very user friendly computer graphing software. It's very intuitive. So here I'm just going to put my general solution. So remember, the general solution have a arbitrary constant c. So how you handle that in the GeoGebra? You do this. So first you put that c. So just put c and press enter. And this will create a slider. So now you can change your c. Okay? And by default it goes from -5 to 5, but you can change it. You can click here, go to setting, and if you go to the slider, maybe I want to go from -10 to 10. Let's do that. Okay, so let's see, -10 to 10. Okay, very good. Now let's enter our function. So it's going to be 1 half y squared equal to e to the x. So you simply use the letter e, and GeoGebra understand, and minus x times e to the power x plus c. Nice function, a nice it looks like a pebble, right? Or I don't know, it looks like a drop of water, right? Okay, very good. So that's the graph of this solution. Now at this moment of time, at this moment, you can look at my c is actually -0.2, right? But I can now use the slider to create an animation. So if I want, I can change the value of c. As I change my value of c, you can see what is the behavior of this graph. So for each value of c, so if I freeze it here, that is a graph of a solution of this differential equation. Of course, it's implicit. Y is given implicitly. So you can see it's not even a function here, right? If it failed the vertical line test. But if you solve for y, typically you are going to get some branches. So here you have the top and the bottom, and maybe something on the side. Okay. So it's like you have like different branches. So we're going to talk about that later. Don't worry. But right now, the initial condition is x is 0 and y is 1. So let's enter that point here, 0 comma 1. That's my point, right? That's my point. So this particular one does not go through this point A. So we have to move this slider so that the graph goes through this point A. Can we do that? So let's increase. Oh, right there. But let me show you. So if I increase my C, see the graph is getting away from that point. So that's not good. It's a solution, but it's not satisfy the initial condition. But I want this graph to go through this point A, which is 0, 1. So it's getting close, getting close, getting close, right there. Oh, not that, right, a little bit above. Let's see if I can do that. Oh, right there. Okay. And you can read it from here. Look at my C. C is negative 0.5, which is negative half. Okay. So this is like a geometric way of finding C. So the geometric way is not very accurate, but it, of course, it gives you a nice visualization and you know what is going on. But many situation, you don't really want geometric, you want the algebraic way, which will give you the exact answer. In the geometric way, you might get some approximate value, is sometimes difficult to find exact answer. Okay. So that's it for today. Always remember that believe yourself and you can always do it. Bye bye.